going to present efficient and scalable paravirtual I/O system, which we also call ELBIS. This is a joint work with my colleagues Nadav, Har'El, Alex, Landau, Muli, Ben-Yehuda, Avishay, Traeger, and Razya, Ladelsky. I will start with a bit of motivation. So why we will actually want to use the Hypervisor, a piece of software, to intercept, interpose in the I/O traffic of the virtual machines. There are many good reasons to do that. Some of them is because we would like to implement software-defined networking, for example. That means that we need to intercept every network frame and maybe encapsulate it in another type of protocol. If we would like to implement file-based images, and expose a block device to a virtual machine that is actually stored as a file in some file system. If we would like to support live migration, full tolerance, we like to run some kind of firewall at the hypervisor level. And there are many, actually not many good reasons not to do that. Just a few. Performance degradation, scalability limitations, more performance degradation, scalability limitation. So basically, if we care about performance, we may run our workload in a bare metal environment. We will have maximum scalability, maximum performance. However, we lose all the flexibility of virtualization. All the nice features I previously mentioned will not be there. On the other hand, we can start using virtualization, run our workload in the virtual machines using emulated I/O devices. And that means we can use any virtualization feature, but performance scalability will not be what we expect from a bare metal environment. We can start using paravirtual I/O in a way that we accept modifying the guest OS or install some drivers in the guest operating system to create a more efficient communication channel between the virtual machine and the hypervisor. We lose a bit of flexibility because we cannot use unmodified operating systems, but we can still interpose in the I/O of all the virtual machines and implement all the nice features that I previously mentioned. We can also go to SRIOV. That means that we give a virtual machine direct access to a physical device. So we significantly improve scalability and performance, but we lose interposition capabilities. The hypervisor is not more involved in the data path. We still have some kind of performance degradation with SRIOV related to interrupts. The hypervisor is usually, or is forced to intercept every interrupt that's coming from a physical device. For that, we have also ELI. It's our previous work presented in ASPLOS last year, in which we enable the physical device to deliver interrupts directly to a running virtual machine without hypervisor interception, but we still have no interposition capabilities. Maximum performance, no interposition. Now, that's why we present and develop ELBIS. ELBIS aims to improve paravirtual I/O performance and achieve levels that are close or similar to SRIOV plus ELI, but we still are able to interpose in the I/O traffic of the virtual machines. So how paravirtual I/O works today? We have a virtual machine, a guest, that starts its execution, at some point start posting I/O requests in a ring queue, just a piece of shared memory between the virtual machine and the hypervisor. And at some point, the guest also needs to notify the hypervisors that new items were posted in the queue. So it sends what we call a request notification. The hypervisor gets the notification, starts consuming all the requests, processing the request. It will probably interact with the physical I/O device. And when it finishes processing the request, it will send the notification back to the virtual machine. Now, the problem with this notification-based mechanism is that it causes a lot of overhead. And why? So the guest starts its execution as a thread running in some core. At some point, this guest performs an I/O request, needs to send a notification from the guest to the host. And the way that hypervisors do this today is by executing a privileged instruction. In the case of KVM, it's actually a PIO instruction. Now, there is a context switch in the processor from the guest context to the hypervisor context. That's what we call an exit. So the hypervisor traps the execution, and if it has some core free for processing the I.O. will start processing this I.O. in another thread in this core. In the meanwhile, we'll resume the execution of the guest until at some point we need to notify the guest that the I.O. was already processed. That means that we need to send a complete notification. And for that, we also need to stop the execution of the guest. In the case of KVM, it's an API, interprocessor interrupt, to force an exit. Once that the guest is not running, we can resume the execution by injecting a virtual interrupt and resuming the guest execution. Now, this chart here only shows you 2 threads, but we usually have 1 thread for each virtual vCPU of each virtual machine. And we usually have 1 thread for each I.O. device. Now, let's try to see now how this model scales when we have a lot of cores, a lot of I.O. bandwidth to virtualize. We have many, many cores running many threads. Some of them will be responsible for the execution of virtual machines. Some of them will be responsible for processing I.O. We will have all these exits for the notifications. So we can start inducing here that something is not going to scale. Now, in particular, all this depends on the host, on the hypervisor thread-based scheduler. So the hypervisor has a bunch of threads to run. It only knows if the threads are ready to run or are waiting for something, but has no idea about all the I.O. requests of the queues. Has no idea how many requests are pending in the queues, no idea for how long all these requests were waiting. Now, a few facts and trends. So far, I hope you understand that notifications cause exits, and this is pure overhead. And there is a trend for multi-core systems with an increasing number of cores per socket. That means that we will be running more and more virtual machines in our physical host. We are having better networks, more bandwidth, lower latencies. And you need to understand that I.O. virtualization is actually a CPU-intensive task. Processing all the I.O. from all the virtual machines will take a lot of CPU resources. And for virtualizing all the bandwidth at lower latencies, we may need more cycles than we have in a single core. That means that based on all these facts and trends, on the paravirtual I.O. model that I previously described, we need a new model that's actually efficient and scalable to all these trends and facts. That's why we present Elvis. So with Elvis, what we propose is to run all the virtual machines in a thread of cores. As usual, schedule all these virtual machines using the thread-based scheduler, but dedicate a set of cores just for I.O. And as opposed to running many threads for I.O., we propose for running a single thread on each I.O. core. The advantage of running a single thread in each I.O. core is that we can implement our own I.O. scheduling policy, what we call the fine-grained I.O. scheduling. And this single thread can actually process requests of many, many virtual machines. The advantage of this approach now are that we can process all the queues of the virtual I.O. devices based on the I.O. activity. That means we can, using this single thread or set of credits, if we have many I.O. cores, based on how many requests are in the queue, how long these requests are waiting there. That means that we can make more smarter decisions to balance between throughput and latency. We get rid of all the thread context switch. And this model also enables what we call exitless communication channel. What I mean with an exitless notification channel, as I previously mentioned, when a virtual machine needs to notify the hypervisor, an exit, a context switch is required. Now, with our model, because we have now a dedicated core with a single thread responsible for processing the I.O. of all the virtual machines, we can actually poll for the queues. We do I.O., process requests, and monitor in the queues and look for new requests. We don't need a notification to wake up any thread. Now, we still need to solve the exit code for the hypervisor to guest, the host to guest notification. And we also solved this issue by extending our previous work on Eli. Again, Eli enables delivering a physical interrupt from a physical device that we use PCI path-through to assign to a virtual machine. Now we are talking about paravirtual I/O, but we extended the same model to send an IPI, interprocessor interrupt, from one core to another core. So now the I/O core can inject a virtual interrupt to another core that is running the guest without requiring an exit. One important thing here to notice is that this extension that we added to Eli actually simulates a new hardware virtualization feature that will be available in future processors called posted interrupts using Intel's terminology, or doorbells interrupts using AMD's terminology. Okay, a bit about the fine-grained I/O scheduling, so you can get some motivation why it's important. So we have a dedicated core running a single thread that will start processing some queue that has all the requests of a virtual machine I/O request. Let's say that this queue is a throughput-intensive queue. While we process this queue, we also monitor the rest of the queues, trying to understand if there are new requests pending there. Let's say that we notice there are pending requests there. We continue running because we like to maximize throughput. We don't want to switch queues too often, but we don't want to starve queues. So when we achieve a maximum amount of data that we process for a given queue, we can switch to another queue, and we continue processing until a point, let's say, that we detect that the queue is stuck. What I mean with the queue is stuck, a queue that has pending requests, but no more requests were added to this queue since the last time we served it. That means that the fact that we are not processing this queue is stopping the workload from making progress. It's not creating more requests. That means that probably the workload is latency-sensitive workload. That means we should switch to this queue as soon as possible, finish all its requests, maybe switch again to some throughput-intensive queue. We again detect that we have a queue stack, but now we don't want to switch queues too often because we will have some impact in throughput. Thus, we continue processing the current queue until we process a minimum amount of data, and so on. We continue switching queues and processing queue. That's, in a few words, how the I/O scheduling works, the fine-grained I/O scheduling work. Now, with Elvis, we also propose dedicating one I/O core for each CPU socket. This is actually a fair request, considering that we are getting more and more cores per socket every year, so this resource overhead is not huge. And network links continue to improving. That means that we, anyway, will need more cores to virtualize more bandwidth at lower latencies. And by dedicating one core per CPU socket, we can also take advantage of the shared last level cache, so we can have I/O requests that are still in the cache when they are sent from the core that is running a virtual machine to the core that is processing I/O. In case that we have a cache miss, we are still in the same socket. That means we are still using the same memory controller. We can take advantage of DDIO technology, in which the device can push I/O data directly into the cache of the processor. And we also propose to deliver the interrupts of the physical device directly to the I/O core, not balance these interrupts across all the cores. That means that these interrupts will not disturb any of the running guests that are running in other cores. That means we can improve locality because we are going to process the interrupt in the same core that's later going to process the I/O, the data. And we can also balance different physical interrupts across different I/O cores, the cores that we dedicated for I/O, by taking advantage of multifunction devices in which we have a different interrupt for each function, or SRIOV adapters in which we can enable SRIOV at the host level, at the hypervisor, not exposing a virtual function to the virtual machine. So each virtual function will have a set of interrupts and can be delivered to different cores. We implemented Elvis on top of the KVM hypervisor using the vhost in-kernel implementation of KVM's paravirtual I/O framework called VirtIO. We use Eli to enable the exit-less replay notification, but also to improve SRIOV performance, because we wanted to see how Elvis performs against the state-of-the-art SRIOV model. We use handy bridge machines equipped with dual socket, 8 cores per socket, dual port 10 gigabit Ethernet adapters with SRIOV capabilities. These were 2 identical servers connected directly with each other. One server was running the virtual machines, and the other server was actually creating load on bare metal. We repeated all our experiments using 1 up to 14 single processor virtual machines, so we can measure scalability. We use, depending on the number of virtual machines, 1 port or 2 ports. And we compare Elvis against 3 different configurations. The first configuration is what we call no interposition. In this configuration, we use SRIOV and LE, so we don't have any hypervisor intervention in the I/O path. And we dedicate a core for each virtual machine, each vCPU which we were running. And we use this configuration to actually measure Elvis efficiency. The closer Elvis is to no interposition, the more efficient Elvis is. Again, we do want interposition, but we need to measure the overhead. We also, of course, compare Elvis against the baseline configuration. There were 2 different baselines. So in all these configurations, paravirtual I/O configurations, we used 1 core for each virtual machine that we were running, and we added 1 or 2 cores for I/O, depending on the number of virtual machines. In the case of Elvis, we dedicate 1 core for each vCPU, or 1 or 2 cores for I/O. In the case of baseline, we dedicated 2 plus 1 cores, n plus 1 cores, or n plus 2 cores that were running all the vCPUs and all the I/O threads, no affinity, no dedication. In the case of baseline plus affinity, we dedicate 1 core for each vCPU, and we pin all the I/O threads to the I/O cores. Now, let's see a bit of results. You can see here how Elvis performed against no interposition, baseline, and baseline plus affinity when we were running netperf TCP stream. This is a throughput-intensive workload. We were using 64-byte message size. And the interesting thing here is that you can notice that Elvis was close or even better than no interposition. Now, as a reminder, when we were using from 1 to 7 virtual machines, we used 1 port and 1 I/O core. From 8 to 13, we used 2 core I/O cores and 2 ports. Now, the reason that Elvis was actually a bit better than no interposition, it's actually related to interrupts and the way that Elvis coalesces interrupts. With an SRIOV device, each virtual function was actually rising 30K interrupts per second, and the number of interrupts per second each virtual function was rising was not related to the number of virtual machines that we were running. In the case of Elvis, the number of virtual interrupts that were injected to the virtual machines was between 4K and 11K. Now, Elvis, when it processed the queues, it batched many requests and sent only 1 virtual interrupt for many requests. Now, as we start adding more and more virtual machines, we start creating more and more batches, bigger batches. That means that as we add more and more virtual machines, the number of virtual interrupts per virtual machine that Elvis was injecting was smaller. That's why you see that Elvis continued improving a bit as we start running more and more virtual machines. Of course, you can see compared to the 2 different baseline configurations that Elvis scaled linearly, perfectly, much better, and significantly much throughput. You can see also that the baseline plus affinity configuration was relatively good when we ran a few number of virtual machines, because it was more close to the Elvis model where we dedicated cores. But at some point that we start running more and more virtual machines, we have more threads, more I/O threads. The I/O threads start starving each other running in the same core, and then baseline actually becomes better than baseline plus affinity. We also, of course, measure latency You can see here that Elvis was able to keep latency close to no interposition or even better. That baseline latency increase as we start adding more and more virtual machines. You don't see here baseline plus affinity because latency starts increasing exponentially, and just for the sake of clarity of the graph, we didn't add it. Now, again, here you are probably asking why Elvis was better than no interposition where we have a few number of virtual machines, and that's related to SRIOV. We noticed that we enable SRIOV latency automatically increase by 22%. We did a simple test in bare metal using the same device when the SRIOV was disabled, and we enable SRIOV bare metal, so we use just a virtual function to go out to the network, and we noticed that the latency increased by 22. We ran also memcached. This was actually kind of worst case scenario for Elvis because after 3 virtual machines, the I/O core was saturated and Elvis was not able to continue increasing with throughput. You can see until when we switch between 7 to 8, when we added an additional I/O core, Elvis continued increasing and scaling. Now, Elvis was up to 30% slower while the I/O core was not saturated and no interposition, but was always better than the baseline, between 30% and 115%. Okay, there are a lot of related work that try to improve paravirtual I/O, propose polling, core dedication to RAM and functionality, exitless interrupts. We extended many of these ideas, integrating them together with the fine-grained I/O scheduling to create a new efficient and scalable paravirtual I/O system. So concluding, most data centers today and cloud providers use paravirtual I/O because they require I/O interposition capabilities to implement all the nice features that I described at the beginning of this presentation. There is a current trend towards multi-core systems with faster networks, and we notice that the current paravirtual I/O model does not match these trends and is inefficient and is not scalable. That's why we propose Elvis to remove all these deficiencies. And a bit of future work, we plan to continue improving the fine-grained I/O schedule to consider also SLAs of the virtual machines, to dynamically allocate I/O cores based on the workload and the system load. And also we like to look into core specialization, what will happen if the I/O core from the architecture perspective is different than the cores that run virtual machines. That concludes the presentation. Thank you very much for listening. Questions?
Hey, JP from VMware. I had a question about your numbers. While it seems like Elvis is performing better than SRIOV in some throughput-wise, and are you running like transmit or receive traffic? Because my question is, if you do receive, seems like
for NetPerf was NetPerf client running in the virtual machine, so it was transmit.
Okay, I think my point is, SRIOV removes the receive copy that So basically, while doing SRIOV, there's the copy of the receive path that you don't have to do, and so I mean, it seems to me like if you do receive workload. I don't think Elvis can outperform SRIOV. Maybe on transmit.
memcached, we also run Apache, and you are invited to look at more benchmarks that are in the paper that also consider receive workloads, and we noticed that Elvis was significantly better than the baseline. Again, the focus here is to improve paravirtual I/O, not to be as efficient and scalable as SRIOV.
Sure.
In some cases, we were able to be better than SRIOV, but that was not our goal.
No, I understand. I just wanted to clarify number.
Okay.
So, thank you.
You're welcome.
Har'El also from VMware. I have a very simple question. So suppose your workload is totally CPU bound. Do you still dedicate a core per socket for just I/O because you don't have I/O? I suppose for this particular case, the answer is no. But we also have workloads that is, for example, partially I/O intensive. Maybe it's I/O only take 20% of a core and you have enough computing request. What do you still waste 80% of a core for I/O and don't use it for CPU computing request? And where do you draw the line?
Okay, so few things here. So first of all, we dedicate one core for each virtual machine to maximize its performance and put the system into extreme situations. You can overcommit CPUs and run many virtual machines in a single core. We did some tests. It didn't change the results. Just the performance of each virtual machine was, half if you were running 2 virtual machines in the same core, or, quarter if you were running 4 virtual machines in the same core. Now, regarding dedicating 1 core for I/O, two things here. One that I didn't mention, but the fine-grained I/O scheduler do something similar to NAPI, in which we switch between polling and notification-based mechanism based on the activity of the I/O queues. So virtual machines that are not actually doing a lot of I/O, we are not going to poll for these notifications. But we propose to dedicate at least 1 core for I/O, because assuming that you were going to run some I/O-intensive workloads in your virtual machine, then you will need all this core to virtualize, again, high bandwidth. We are talking about 10, 20 gigabit Ethernet at lower latencies. Hope this answers your question.
Wenji from Fermilab. And when you dedicate 1 I/O core for your virtual machine, then once your virtual machine is...
For many virtual machines, okay? It was 1 I/O core for all, or 2 I/O core for all the system. Each virtual machine, we were multiplexing this core against multiple virtual machines.
So then your dedicated core is manually handled, or is automatically handled by your software? So if your virtual machine is migrate, and then your I/O, the core is also automatically configured to other cores.
So right now, our implementation, it's more static, where we always dedicate 1 core or 2 cores for I/O. Again, so you will always have 1 or 2, but that's the future work. We are looking into how we can extend, or how we can allocate and deallocate I/O cores based on the activity of the virtual machines and the load that they generate.
Okay, thank you.
Okay, let's thank our speaker. Thank you very much.